Now on the agenda is again Hannes. He will present the Nostradamus project that builds the EU quantum communication testing infrastructure. Hannes, the floor is yours. Thank you.
Okay, thank you. Hello again. I will give a brief overview now on the Nostradamus project, which was started at the beginning of this year. So it's really about setting up a testing and evaluation infrastructure for EuroQCI, and specifically for testing and certifying QKD products. So it's really Nostradamus itself will not be the final evaluation lab. That will be somewhere else. However, we should define the procedures and evaluation criteria which are then employed in the certification lab. Why we need this is simply that if you buy now a QKD box nowadays, you can do that. You have to somehow trust the manufacturer, what it does, and that it's actually secure. So it will say on the box something, it will say, okay, I can generate so many bits at different distances, at different attenuation. But you as a customer, it's sometimes very hard to basically verify those claims. So this is really why we need certification. So those systems then will go through a rigorous evaluation program, and if they basically pass all the tests, then a certification agency, which might be a national security agency, will basically put a stamp on it and say, yeah, it basically does what it says on the box, and it's also secure. It basically implements all the security requirements that are needed and also defined in some maybe protection profile. It should also, what the project should do, that's in the second point, it should basically offer those initial evaluation services. I don't know why you don't see the whole slide. Elias, do you know why it's a bit? Oh, the slides is somehow cropped. But I don't know if you... Okay, well. Oh yeah, now it's better. Yeah, thank you. It should basically also offer those initial evaluation services. So basically, that's especially for the QKD manufacturer. If you have a product and you're basically willing to maybe do some pre-evaluation, please come to the Nostradamus project in maybe about a year's time, when we have the first evaluation procedures in place, and we will basically then perform those tests on your devices. They will not be certified at that point, but nevertheless, we can give you basically feedback on how they performed. So, but let's come back to this implementation security, why we actually do it or need it. So this was the first experimental QKD setup back in 1989, so about 5 years after the famous BB84 protocol. So the first QKD protocol was actually theoretically described. That was the setup. So yeah, typical bench top setup. Some of the components that look a bit more old-fashioned than nowadays, but nevertheless it did the same thing. So it was polarization encoded QKD. Two issues with it. First of all, protocol implementation. So in the BB84 protocols, it says that you should basically choose your basis state and your bit that you want to encode completely randomly. Of course, as an experimenter, it's not always so easy, especially at that time. I think there were no QRNGs, so quantum random number generators available. So people just went the easy way, and they were basically just rotating the polarizer disk, which basically ended up in a key which is 0101010101. Again, not safe, because anybody who knows that can then just apply the same sequence and has the key. So this is really where this experiment, I mean, of course, it was not targeting this, but this would basically fail a kind of a protocol implementation, where you don't follow exactly the QKD protocol as it is described. And the second one is also physical implementation. You have to be really careful, so that there are basically no side channels. So there's no other piece of equipment in your setup that basically gives additional information out except this encoded photon that comes out. That's the only thing bit of information should be coming out, because that is protected by quantum mechanics. Nobody can learn the key. In this setup, which is quite interesting, so depending on where this polarizer, this encoding polarizer was, it basically made a different sound, yeah? So it meant a click, clack, cluck or whatever. So if you were listening to it, you could again get the key out of it. So again, this is just showing you that it's really important to basically do a proper protocol implementation and also a proper physical implementation of your device. And of course, security is a trust issue. If somebody basically says, I have now implemented everything properly, you still would like some third party to verify that and then basically certify it. And this is exactly what Nostradamus is about, to basically check the existing commercial systems for protocol implementation and physical implementation. It's a 4-year project that started in 2024. We have it in different phases. So since there are many possible attacks, side channel attacks on QKD system, we will do some prioritization. We have done that. So we will basically look at the most urgent ones before, try to implement or come up with a testing procedure, then implement that, offer that as a service, and then in the next year go to the next set of possible side channel attacks. We are working closely with there's only 3 main partners, Deutsche Telekom, EIT, and Thales, but we have a lot of subcontractors from the scientific community. We also have GRNet and the Ministry of Digital Governance, also part here from Greece. Also some metrology companies who basically support us in this endeavor. Plus there is also IT labs, which are basically specialized already in security evaluation of standard classical cryptographic products, which again help us with this setting up those testing procedures. So what we did, at the moment, beginning of the project, we basically went through the whole literature on QKD, and we're looking for all published side channel attacks and countermeasures, so how you can basically secure your system against those side channel attacks. The result is, so there were 6 general side channel attacks, which are basically used in DV and CV QKD. Those are mainly kind of Trojan horses attacks, where you basically shine a laser light into your transmitter, and on the reflected light that comes out, you basically try to infer what's the state of the polarizer or of the modulator. Then there are a couple of more only on CV QKD systems, quite a lot on DV QKD systems. This is mainly the detector part, because the detector part by definition has to be open, because it has to receive the photon, so it's quite easy to basically shine some other light into it as well, and either gauge the state of it, or even in some cases on some special type of detectors, you really can take over them and make them click on demand. So you can really say, okay, I want that detector to click now. So you have to make sure you can be safe against that. Then there are some other vulnerabilities. Again, this is more than if you don't implement the protocol correctly. And there's a lot of countermeasures as well now that manufacturers could basically use to implement to basically be secure against some or all of those attacks. First of all, we are looking only on prepare and measure systems. So those are the systems which are basically, you have a transmitter and the receiver station. So the transmitter prepares a photon, encodes a photon, sends it over, it's decoded and detected. We have not done that. We have not done the analysis for entanglement-based systems or MDI QKD systems or measurement device independent systems. It's quite interesting, those two, because they offer some inherently more security, or basically less or more resilient against some side channel attacks. For example, measurement devices independent QKD systems are safe against all detector attacks, because you really give the detector to a potential eavesdropper, to a potential adversary. They can basically manipulate as much as they want it, and you can still extract a secure key. However, those systems are not yet and they are commercialized, but not so proliferant like other ones. So at the moment they have not been looked at, should be in the future though. We were also constricting ourselves to EU27 manufacturers, and we also were, for the prioritization, looking, okay, what are the most important attacks to consider? And those are the ones which have been demonstrated in experimental setups, or which are at least viable. So basically all the components are available. Because in theory, if you really want to basically secure it completely, you would have to assume that an adversary has a fully fledged quantum computer, yeah, which we just saw before. Probably nobody has by now. Maybe maybe some military labs, but it's very unlikely. So it's really hard also to basically then test or certify a system that they are secure against a fully fledged quantum computer attack if you cannot actually build this attack. So at the moment we have to go a bit of a practical approach here and really do what we think is most likely that an adversary has. And the same thing we do also with the countermeasures. We basically looked, okay, which ones are really so good that they completely close the loophole or impedes the attack, at least in connection with another one. And this is what will be set up or implemented now in the first round. Unfortunately, I cannot tell you, because it's a bit of restricted content, so I cannot tell you exactly which ones they are, but once we hopefully have implemented or have a methodology devised, then we can publish those results. And just very briefly, this is this kind of circle of security assurance by evaluation. So there's one kind of assurance level specified, how safe your system is. Then the manufacturer will produce that. They will basically, based on a protection profile, put a target of evaluation down with documentation. This then device and the documents go to the evaluator lab, which basically does run the tests, and then it has to be certified if they pass all the tests by some certification authority, which might be an NSA. And what I can tell you now, this was just coming out recently. So for the EuroQCI, for those systems, the accreditation lab or evaluation lab will be hosted by the Joint Research Center in Ispra in Italy. I mean, they're already quite involved in QKD and EuroQCI, and they will basically host the final evaluation lab. So they will basically take from this project the procedures and then implement it in this lab there. We do basically two types of testing, or we develop the procedures for two types of testing. The first one is functional testing. This is more like, okay, looking at does the product actually do what it says on the box, so does it provide the right amount of key? What is the uptime, downtime of the systems? Does it provide the right interfaces, for example, to key management or to SDNs? And this will be standardized and can be then tested on the system. And then, of course, the main tests will be then those vulnerability analysis, where we basically will implement the different side channel attacks on the system and see if the system is actually secure, or at least then shuts down and says, okay, there has been an attack detected, I will no longer produce a key. And just a last slide here. We will mainly look at the quantum channel. So since it's a cryptographic system, there's a lot of side channels, for example, also on the FPGA you implement, radiation that might come out. We are not looking at those things. Those things should already been anyway done in other classical examples, and we will basically only focus on the quantum channel. So what are the additional side channels that are due to the fact that you have basically this quantum link on the bottom? And yeah, some challenges. I think it's rather new. So there has been only a few groups working worldwide on this kind of quantum hacking. So I think it's hard to find people who have the know-how. Then, yeah, some attacks, as I said, have been only described on paper. So they are theoretical attacks, and it's hard to basically find the right hardware at the moment to basically implement those attacks. So one has to go, as I said, more a practical approach to solve that and really see, okay, what is most likely an adversary has available, and basically try to secure the system against those attacks. And of course, we need also a lot of test vehicles from different suppliers having implemented different QKD protocols to basically check them for possible side channels and see again, yeah, maybe which implementations are maybe more suitable to secure than others. And with this, thank you very much.